So a vector is really an abstract concept that just represents something with a magnitude and a direction. We have different ways of representing that we can then manipulate using math and geometry, and that's kind of what this topic is about, vector representations. A common confusion, a common pitfall is to think that one or the other of the main two representations we're looking at here really is like what a vector is. But I would say no, a vector is actually more abstract than either one. It might be arguably, the idea of a vector might be more closely tied to the magnitude angle representation. And it says here on the slide that, as a key concept, that a vector is represented by a, and that represents the magnitude, and theta sub a, which represents the angle. And I've drawn that up here in my whiteboard section. I've just put the label a, again, to represent magnitude. So one point of confusion here is a kind of like is the name of this vector, but it also represents the magnitude. The subtlety is if I really want to refer to the vector as a whole, I'd write a with the arrow over it. If I'm just referring to the magnitude, I'm more likely going to write a. There's sometimes some ambiguity though, like in a picture, it's customary to not include arrows, or you don't have to include arrows, so I sometimes don't. And in that sense, it could either be referring to the magnitude of this vector or the name of the vector. Again, that can be a bit ambiguous. But here, I'm in the pictures I've drawn here, I'm meaning this a to represent the magnitude of this vector that is named a. And then theta here represents the angle. And over here, I called it theta sub a. I think I didn't put the sub a over here just to indicate it is optional. If you have an angle, if you only have one vector in a problem, you don't necessarily need to subscript to describe that angle. And maybe it's 45 degrees and you just put the number there, right? That is okay as well. The other major way of representing vectors is using components. So the component representation, and on the slide I've got that listed here as a key concept that says vector A is represented by a sub x and a sub y, and this drawing over here shows the vector A and its two components a sub x and a sub y, and I've just kind of put them in as line segments, which may or may not be correct, because really components do have direction and can be negative in some coordinate system. Like a y component in that sense could point up as this one does, but for a different vector could wind up pointing down, and usually in a Cartesian coordinate system you would describe that as a negative y component. So it's also customary in that sense. The way I drew it here by hand is I kind of copied the same vector I had before, because I'm really looking at like just a different representation of the same vector, but then I drew in the two components with arrows themselves to indicate that these are both positive components in that sense. The components can, in that sense, actually be thought of as themselves being vectors as well, but you don't necessarily have to, because like if I just say the component is equal to this value, that turns out not really to be a full vector. So again, this may be a little bit ambiguous in that sense. I think the reason I drew it this way here is it's a little less confusing to think of them also as being vectors, because they really are just components of this A vector here. Now the last thing I have on this key concept slide are some formulas, and it turns out, I mean, you could say, oh boy, more formulas to memorize, but it turns out you might already know these, because if I redraw the vector I have here, and I might not get it perfect, I'm going to draw it a little bit bigger, and actually maybe I don't even need to draw the arrow, but I'm going to draw what I like to call the component triangle. In other words, if this represents the magnitude of that vector A, which is kind of part of the magnitude angle representation, and if this line segment down here is the x component, and if this line segment is the y component, and those of course comprise the component representation, but from the angle magnitude representation there is also that angle right there. And if you remember basic trigonometry, the cosine of theta should be equal to adjacent over hypotenuse, so that should be a sub x divided by a. And if you look at what I've written here, if you multiplied this formula both sides by a, you would basically get this formula here on the key concepts page. And in a similar way, sine of theta is equal to opposite over hypotenuse, so that one would be a sub y over a. And if you multiply both sides by a, you get this second equation I have on this kind of second to last line of the key concepts. These are the two equations that kind of given a magnitude and an angle can let you calculate the components. And of course, it's also handy sometimes to be able to do the opposite. given components can I go and calculate the magnitude and the angle? And the magnitude is fairly straightforward. This might make sense based on this same triangle here. If this is a right triangle, if I add the two components squares and then square root them, that's basically what you do with the Pythagorean theorem. You get the length of the hypotenuse, and that's basically this formula right here. So really, all these formulas kind of relate to thinking about the components as together with the vector creating a right triangle that I like to call the component triangle. And this last formula here, I like to say that the tangent of the angle, that's kind of analogous to what I did with cosine and sine here. The tangent would be opposite over adjacent, so AY over AX. This is the formula that is generally used if you want to find the angle. Usually what you do is you would say theta is equal to tangent inverse of the ratio of these two components, but I didn't state that here because sometimes depending on what quadrant the vector is pointing in, that may or may not work. And so I usually draw a picture and figure out like, well, is that the correct angle, or maybe I need to like add or subtract like 180 degrees from it usually is what winds up happening. So hopefully we'll see something like that when we look at some of the examples here.